So we were talking about bad things with computers and software, unfortunately. Bad things have happened. You wrote an essay on that as well. You had some nice thoughts. And we eventually settled on at least we should be testing our programs, right? In some form, we should be testing them to make sure that we can trust them at least a little bit, right? So we talked about how to make a test, and you just want to make as many of those as you can for every program that you write, more or less, all right? There's more that you can do, though. There's ways to make software that is perfect. Software that is actually correct from the start, that cannot at all be messed with. All right, so there's ways to do that. And here are some ways. I guess I can make this font size bigger. Cool. So here are some ways to make correct software from the beginning without any bad things ever having the potential of happening, which is cool. You can write programs that either check their outputs every time they make outputs, like they got tests baked into the program. You can also write redundant programs, and by that I mean write two programs, like have, like, I don't know, maybe you've got, let's think about this in terms of something. Let's say that we want to program airplane autopilot or something, and that's very important that we don't want to crash the plane, right? So what you can do is you can have one group of software engineers go work on one version of the autopilot software, and have a completely separate group work on another version of the same software. So they'll take the same inputs, try to produce the same outputs, and then you run both. You put both inside the airplane, and then you see, like, do they agree? Each time you feed them inputs, do they agree on their outputs? And if they do, then you can trust them. And then if they don't, maybe then the pilot has to take over. So that's kind of neat, right? Just have two people do the same thing, and then have them fight for the right answer, see if they agree on the right answer. There's that. You can also do mathematical proofs. There's a way to turn computer programs into math and prove that your program cannot possibly do anything bad. There are proof assistants that help you do that. The most popular one is called Rock. It's got a little cute mascot and everything. But like, here's kind of how you would do that. Let's say we've got some Python code, like x equals 42, simple Python code. X equals x plus 1. I can prove to you some stuff about this code, right? Can you imagine, like, what goes on when you're proving something about this code? Well, it's kind of like what's true after each line is run. So, like, what's true after this line is run? You can prove, right, that, well, x is a variable. It's been made now. It's holding 42. Yeah? Does that kind of make sense? And then this line, what does that do? Knowing that x was 42 before, now that this line runs, do you see how you can prove? You can find probably a way to prove that x is going to be for sure 43 by the time that second line's finished. You can do that for more complicated code. It gets a little weird, but you can prove stuff like this, like x is for sure 43 here. Does that make sense? That's pretty cool. It gets more complicated, of course, when you insert like loops and ifs and things, but it's all still possible. You can also have an analyzer. There's little analyses that you can run on your programs that kind of did some proofs before, and they run the program in math and see what kinds of properties would arise out of the program. So you can, like, it would output like little ideas like, I'm not sure that x is going to be 43 here, but I'm sure that it's going to be at least bigger than 42 or something. Like, you can analyze your program and see if there's any issues, or like security leaks. A lot of people make security-based analyzers. Like, is this program, I don't trust it. If I run it right now, is it going to talk to the internet? I don't want it to. Like, that's a thing that you can do. All right. So these kind of go hand in hand. Like, you can prove that an analyzer is correct, or you can write a proof about your program. And then finally, there's also some specification languages. There's ways to describe in math, like, what a program should do, and then you can go hand off, like, the problem to a software engineer, to a programmer, and see if they did it right with respect to the specification. So that's always something that's difficult. So you have to, like, somehow write down either in English or in math, like, what a program should do, right, if you're the manager. And that's kind of hard sometimes. Like, here's a potential requirement of a program, right, that you give to somebody. Requirement. Like, the output of the program should always be greater than or equal to 42, something like that. I don't know. Like, that's a thing that could be your specification. There's languages that will let you do that. Like, it's like a programming language just for specifying programs and how they should be. It's called Z because it's European. And then, yeah, then you use go use an analyzer, make sure that this gets spat out. Go write a proof to make sure that this is always true. So no matter what you're doing, at the end of the day, you do need a specification first. You need to have a list of what you need to do. I hope that makes sense for everybody. I'm giving you the specification when I give you programming assignments, yeah. But you have to get that specification right up front, right? Because otherwise, if you give a bad specification and you write the program and you prove that it's correct with respect to that bad specification, now there are issues, right? So you have to specify upfront exactly what your program does and or can do. And then the sad part is, if your specification was wrong, the entire program, it's also wrong now. So there's new ways to mess up, unfortunately. But that's kind of what people do with mission critical software, like probably autopilot for airplanes, stuff like that. All right, any questions about that? Those are kind of little ideas that you might study one day. Cool to think about. In that vein, let's keep talking about planes. I have a little anecdote here. We made a little box that goes in planes that's supposed to make them safer. It's called the Traffic Collision Avoidance System, or TCAS for short. And it's a little box, and it lets planes know if they're about to hit each other, which is very useful, right? So we made these little boxes. We ordered everyone to put them in all their planes, and it tells the planes if the boxes ever notice that the planes are too close to each other, they're coming in at the same, one's going this way, one's going that way, and then their altitudes are not that different. It tells the pilots what to do of each plane. The boxes talk to each other as well. So here's the two planes, boop, and the TCAS, I guess, system says to one plane, you should go up, you should go down, and then we will resolve the problem. All right, so that's a box that we made. We've ordered it to go inside of every plane, the TCAS system. And it's a good idea, right? It keeps everybody happy. But sadly, when this box first started coming out, the first versions of this box thought that planes that were not at all going to crash were going to crash. And so it kind of cried wolf. And a lot of people, because of that, stopped trusting the box initially. That's not good, all right? Eventually, they made it better, and it's perfectly accurate now. You have to follow its orders if it tells you to do something. But unfortunately, a collision happened due to this box because one pilot, they followed the TCAS system saying to go up or something, and then the other pilot did not. They disagreed, or they followed the instructions of the air traffic controller, the person on the ground telling planes what to do. They followed their instructions and they probably also told them to go up. So one followed the box, one did not follow the box, and they ended up crashing because of that. That's very unfortunate. I don't remember the full story, but now everyone, because of this, they made it work well enough. Now everybody has to trust the box. They all have to disobey the human and trust the TCAS system, telling you what to do. You must go up if it tells you to go up. You cannot do anything else. And that's prevented a lot of issues going forward, which is really nice. But it have some bugs at the start, and people stopped trusting it. But now, I guess we're kind of forced to trust it. So that's an interesting story, right? Now we have to disobey a human and trust a machine for our lives. Any thoughts about that? Questions, ideas? That's a little weird. I don't know. Do you trust a machine more than a human? I don't know. In this situation, maybe it is a good idea. So I do have a question. I want to hear your thought no matter what now. So please go to the written ice page because I have a question for us here. And I'll stop attendance if I can remember after this is finished. But I want you to get into little groups, please. As usual, say hello, and then talk about this question. All right, so here's a little mini debate for us. The question is, do we depend on computers too much? I just showed you some ideas. We talked about the bad stuff with computers. We talked about how to make things safe, and we talked about how we're now forced to trust a machine over a human's advice. Does that mean we depend on computers too much? Why or why not? So what I'd like you to do, I'm not going to give you a stance, but please as a group, write down at least one good argument for, yes, we do trust computers too much. Here's why. And then one good argument against. We don't trust computers enough, maybe. We should trust them. They're better than humans for this and this reason. All right. So at least one argument on each side. Try to do more if you can. But I think that's what I want to ask. Are there any questions about the question? Please go off, have a good discussion, and we'll come back and see what you're thinking. Do we all do one of each and then stop? I need to say like 5 of each next time. But I'll give you another couple minutes if you're still thinking about things and typing. At least one of each. Definitely can do more. Alright, 30 more seconds. Press that submit button, finish that thought, and then we will discuss. All right. Well, let's see what we're thinking. What are our good reasons why we either do trust computers too much, or we don't, or we depend on them too much. All right, let's read a few of these. Let's do this one. So start at 53. We do trust computers too much because we do everything on a computer. We save our passwords inside of a computer. Yeah, we get information from it. That's true. And you're implying that that's a bad thing, probably, I assume. Like that's like somebody can easily hack our password, maybe, if they get control of our computer. Maybe we don't trust it enough because we still have people doing jobs that a computer could do. That's true. Yeah. If one day when AI gets better, we can save people's backs and things like that. They've already made like great strides in that area for sure. But yeah, well, these are good ideas. Let's go down to just zoom to the bottom, maybe 56 and 57. So all right, I don't think that we rely on computers too much. A lot of good is coming from completing elements of daily life digitally. Like, I'm all for Zoom meetings where I don't have to come into work. I love that. That's true. Very nice ideas. A good counter argument is that it's easier to hack or harm systems digitally. That's true. It's very hard. Like, not many people are going in and robbing banks these days, but you can imagine that it's very easy to, like, people are stealing cryptocurrency all day long. Like, it's easy, like, when you're across the ocean to do something nefarious. And that's allowed now because we are all connected to each other. All the computers are connected through the internet. Yeah, something that is not like that would be more resistant to attack. Good. All right, let's do one more. 57. Yes, we over rely on it because we do normal things like robot vacuum or AI to do assignments. So yeah, maybe yes, we depend on it too much because we could have been doing things ourselves. Like we're becoming dumber or something. So yeah, don't have AI do your assignments, please. And then no, we don't believe or we don't trust or rely on computers enough because there's still things that people do themselves. I guess that's true. Yeah, there's things that could be automated if we just let a computer do it. Makes sense to me. Nice. So good thoughts. Thank you for that. And then I promised to stop that. Cool. So yeah, that's just something we have to grapple with as citizens of the world today. Well, we can always, when we're sick, we can always ask our boys. I guess maybe with the air traffic control example, like if that's saving people's lives, maybe we should definitely depend on computers more. I'm not sure, but I'm of course biased up here as a computer science teacher. But yeah, but you can ask a question to our boys of like, should we trust computers? Should we not? Oops. So what would Kant do? He'd probably ask a question with the word always in it, right? He'd be like, should we always be using computers to solve our problems? And Kant, again, always for individual liberties, personal freedom, he would probably say like, all right, if you don't want to use a computer to do this thing, you're sure not required to. So that's the thing. I think Kant would be pro-choice for computers, right? You don't have to use one if you don't want to. And then a utilitarian would just pose the question of like pro and con list. What's increasing the total utility of the universe? I think a utilitarian would probably say like, yeah, we should like rely on computers even more than we are right now because they're going to improve our lives. If we make robots that do a lot of things that people are doing manually right now, we could like save people's health, stuff like that. All right. So yeah, I think that's some good ideas, right? When in doubt, you can always ask, always look back to our ethical theories and ask our proponents of each of them. All right. So yeah, one last slide for this set of slides at least. Like, if we do claim that computers make us safer, how do they? How do they make us safer? We have probably a few ideas in our mind already, but I've got a few listed here, right? We are forced to drive cars around in Fresno, right? Because they got rid of all the like light rail that there used to be in the past or whatever. Cars are safer than they used to be because of technology, right? And we put tiny computer chips in cars starting in the 90s or something, right? ABS was the first big deal. right? That's letting you brake without having to like skid. That was a hard thing to do. Like you were supposed to like, I remember, did they still teach that to you guys in driver's ed? Like if you have a car without ABS, you have to like not like hold in the brakes. You have to like tap it down, keep it going so that it doesn't skid. No, they stopped telling us that. I don't know. Cool. But that's a thing. Like ABS is doing that for us. It'll let us stop sooner and not like hurt people or get hurt ourselves. And then the check engine light, there's a computer, even in older cars, there's a computer that's like running little tests as you turn your car on and as it's running to like see if there's a misfire or something, and it tells you like you should go take your car in right now, and that's going to help everybody on the road be safer, right? So your car does not like catch fire or something. So that's very helpful. Airplanes, how do they make us safer? Like after we've started adding in like digital electronics and software, you got the TCAS system. You've got autopilot, keeping pilots from getting too tired, things like that, when it's just go straight for a while. And yeah, that's the thing. You've got home security systems. People love to put cameras up, like the Ring cameras and things like that. And that, like, in theory, is going to like make a potential thief that comes to your door and sees the camera, like makes them think twice, in theory. I guess if you wanted a security system before like the digital age, you had to buy a dog. I guess people still do that. And yeah, you've got passcodes on your phone. Usually those are protecting you from like if somebody steals your phone from getting in and getting access to like all of your apps that you have logged in on, right? Including your banking app. Like you can also go to your bank online. That used to not be a thing. Right? You had to go into your bank and like give them money or get money or transfer things. Like now we can all do it online and get paid just digitally, essentially. That's how I get paid, right? Go straight to the bank account. No having to fiddle with checks or anything. And like that helps keep things safe. You got a bunch of fancy password ways to like get in and stay safe, like two-factor authentication so that you like a notification comes up on your phone, things like that. All right, so I guess I am a little biased as a computer science instructor, but I think that things are getting better. Software is helping our lives in some small way. All right. So yeah, that's those slides. Are we ready for a completely new topic? Any comments, thoughts about anything before we start a different topic? Do we trust computers? I guess we're all sitting in front of one right now. At least a little bit. All right, let's next talk about AI. Might as well. We made it. So we all know this term by now, but it used to be like, just think a few years ago, me teaching CSCI 1, like not a lot of people probably understood the implications of it, but now of course we do because it's out in the open. We know a lot about it. So let's try to talk a little bit about the nitty gritty. I'll try to teach you like how artificial intelligence is working at like a high level, and hopefully more than you already know. And the first thing that I need to talk about is what's called Moore's Law. Have any of us heard of that? It's called Moore's Law. It's a way to talk about how computers get fast. So like, I'll answer this question. How fast are computers getting faster? All right, it's a weird question to ask, but it does make sense. I hope you can see it. Because computers are like, we're making bigger and bigger ones, right? That have more speed. We have fancier and fancier graphics cards every year, right? They're all thousands of dollars. But Moore's Law was, it's not really like a law. It's more of a theory, right? It's more of an observation, honestly. It's an observation by a man named Gordon Moore, who was the co-founder of Intel, very popular company, right? He noticed back in the either late 50s or early 60s, he was like, we're getting better at making transistors smaller. Remember that word from the first day of class? Transistor is just like the reason we have computers that are this small right now. They're the tiny little building block of computation, right? All of our processors are made out of a bunch of little transistors. And Gordon Moore noticed that the transistors on a chip, like in a CPU or something, they are tending to double every about 2 years. The number of transistors doubles. So like it's an exponential increase. Like year one, there's one transistor. I don't know. Year two, there's 2 transistors. Year 3, there's 4 transistors. Obviously, they did more than that, but you got to get the idea, right? 4, and all the way to 8 for year 4. It is a exponential increasing graph, something like that. All right. So you notice that, And that used to mean, like, back up well into, like, from the 60s onwards to the early 2000s, that also meant that computers got twice as fast as well. We heard of like terms to talk about the speed of a computer, like I have a 4 gigahertz processor. We heard of that before. We've like built a computer or something. Maybe we've seen that. But that just means that the processor can run 4 billion, the giga means billion, 4 billion instructions every second, where an instruction is some small piece of computation. And we've kind of maxed out around 4. If you've looked at CPUs over the years, like 4 is about as good as we can do right now. But for a while, computers were getting faster and faster. It was like megahertz, like kilohertz, megahertz. Now we're in the gigahertz range. And like in the early 2000s, about 4 is where we stopped, because like it just took too much power to make it go any faster, and it got too hot as well. And so it's very hard to cool anything past this. So we have still a bunch of transistors increasing. The number's increasing, but we had to change like routes. We can't make computers faster. But legitimately for a while, it's like, why even, if you were a software developer, it's like, I don't need to like make my software faster. I'll just wait 2 years, and then everybody will have faster computers that will run twice as fast. That was an interesting solution to those problems. But now we're kind of stuck. So that's really funny to think about, I think. But yeah, it got to be that like they're running so quickly that it's hard to power something going faster than 4 gigahertz, and then also to cool it down. All right, so that's the thing. We hit a power wall, we say, and that's when a bunch of multi-core processors started getting made. We know that word, right? We've seen a bunch of, like, I have a 4-core processor, I have a 6-core processor inside of my computer. I think this one's 4, but I can only imagine what are in those big computers, maybe like 12 core or something. I don't know, at least 6 probably. But yeah, then we started packing a bunch of transistors together, but we didn't like, what's the word? We stopped making them faster. We just put a bunch of CPUs in our CPU, essentially. That's what happened. And yeah, there's that. And soon enough, Moore's law is not going to hold anymore. So this is what we've got right now. It's essentially like, if we want to double the transistors in our CPU chips, we're just going to put a bunch of tiny CPU cores inside of our chips. Like each one of them, like I'm going to put 4 cores, and each of them are going to be like 2.5 gigahertz or something, and they're going to run like, you can run 4 programs at the same time with a 4-core processor. That's kind of what that means. But yeah, we can still get, if we do it this way, like add cores, we can still add more transistors. But soon enough, Moore's law is going to fail. It's been holding steady for a long time, but now if we try to make CPUs much smaller, we run into quantum effects, because the transistors are so tiny they can only hold a few electrons, and those electrons are jumping away, which is really cool to think about. But Moore's law has been holding for a while. It's about to not hold much longer. All right, so we have to find a new way to make computers. But yeah, here's the old stuff. Here's a graph. So on the x-axis is dates every 2 years, and then on the y-axis is number of transistors in a chip. All right, and this is a log scale. So you see how it's jumping up by like powers of 10. And so if the trend is a line, and I think you can see that it's a line, that means really, because the y-axis is a log scale, it means exponential increase. It means doubling, all right? So that's pretty cool. Dun, dun, dun. So yes, that is interesting. So here's some of the first CPU chips. Like Intel was on the scene back in the day. Intel 404808. Not even 5,000 transistors in that chip. Is probably very slow, but it did some work. Somebody wanted it to do stuff. And yeah, every 2 years, you see how it's getting about twice as fast. And then also the number of transistors is getting bigger as well. All right, so this is transistor count. So the transistor count by the 80s is into the hundreds of thousands. These are very interesting processors, right? Very, very popular things. Motorola 6800, very popular competitor to Intel. And you see that ARM processors are on the scene back in the mid-80s, competing at the same time with Intel processors that had like 50 times more transistors. So ARM processors were meant to be small and simple and fast, and they were just as fast. They were competing with Intel processors that were like almost like 50 times as many transistors. So that was really cool. ARM started back then for that reason. And then, yeah, you start getting fancier and fancier. The Pentium processors was a cool line back in the day in the early 90s. And like then we're at the level of millions of transistors, and it's getting faster and faster. We're at the 500 megahertz stage right now. Pentium 3, Pentium 4, you got hundreds of millions, transistors. It's getting super fast. And that's about when we clocked out of speed, like at 4 gigahertz around then, early 2000s. And then you see what happened to keep increasing the number of transistors. Over here, now we're at 1 billion. To keep being able to increase transistors, we started introducing multi-core chips. See that? Core 2, Core i7, all those things. So we started adding more cores rather than making one CPU more beefy. Just became impossible. And then nowadays, I'll probably have to upgrade this graph. We can have 72 core machines if you want. And I'm sure they've made more than that in like supercomputers. But we're at the level of 50 billion transistors in a chip. Crazy to think about. But yeah, that is the trend line. It is still doubling, but eventually it's just not going to work much longer. But yeah, that's good news for us. We don't have to buy a new computer every 2 years, I guess. But that is Moore's law in a nutshell. Computers are tending to increase in transistor size every 2 years, and that makes them more powerful in some sense of the word. All right, so there's that. I will keep this handy-dandy trend line. Yeah, I love that PowerPoint lets me do that now. Make a perfect line. And with that, we're ready to talk about artificial intelligence. Because 20 years ago, right, computers were slower. We couldn't really do much, but now we have faster computers. And we can do more processing things, right? So let's talk about artificial intelligence. It's the idea of making computers smart, right? Virtual smart things. So it's like teaching computers to think. I'll teach you how they do that. And how are they actually good at it? How are they doing anything at all? So let's talk about all these things, right? So I guess the first thing I should do is so we're on the same page. Let's define AI, artificial intelligence, AI for short. It's just when you have computers doing things that usually are attributed to humans in terms of thought. Those machines are thinking in some way, and so if we want to expand on that, they are perceiving their environment in some sense. They're getting some kind of input that seems like something that a human would get, and then they're making choices based on what they see, what they get to achieve their goals. So if you think about this in terms of a robot, you got a bunch of cool robots that are being made that are powered by artificial intelligence. They've got sensors, right? They've got video sensors, audio sensors, gyroscopes. They can understand which way is up and down, stuff like that. And they can be programmed with I need you to jump on this box or something that's their goal or something. And then they can make choices to navigate the world around them to get to where they need to go. All right, jump just as much as they need to. That's very utilitarian, kind of they're doing what they need to do to get what they want. It's a little scary to think about. And there's a bunch of different subfields of AI though. It's not just one thing. Robotics, I would say for sure, is one subfield of AI. Boston Dynamics is a crazy little company that makes things that look like this, that are weird. They have interesting videos on their YouTube channel if you go look into that. But they have fancy robots that can do cool things. I would also say that machine learning is a subfield of AI. Machine learning is used for a lot of things, like the facial recognition to unlock your phone, stuff like that. Neural networks, which is the thing that powers ChatGPT and other things like that. Those are they came out of the idea of machine learning, all right? And then finally, honestly, at the end of the day, if you read enough about artificial intelligence and or machine learning, you will learn that it's all just a buzzword. It's all just glorified statistics at the end of the day. That's all artificial intelligence is. It's we're going to do some statistics to figure out the right thing to do. So if you learn statistics, you will be in good shape if you ever need to get into AI, all right? I think that's what I want to start with. Now we're on the same page, so let's look at some examples. Let's have some examples of AI. I'll start with some simple ones, then we'll talk about how do neural networks work, because I need to teach you how ChatGPT works, at least at a small level. So, all right, probably the first use of artificial intelligence that became used in daily life was you bought digital cameras back in the mid-2000s, and onwards, before smartphones became popular. And on those cameras, I assume if you buy one today, they still have it, but they drew little squares around people's heads, and they could figure out if somebody blinked. Did we ever have one of those? Did we inherit one of those older cameras that does that? They probably still make them. I honestly don't know. I don't use anything other than my smartphone for a camera. But this was a thing, all right? And so this is facial recognition, first of all, detect the faces, and then also blink detection has to detect the eyes and see if somebody's blinking, all right? So this is a machine learning technique, all right? That's something. So that's what a camera did. It's like, all right, have a bunch of people pose, and like it can see, first of all, it can find the heads, and then from that, it can find the eyes and see if they are open or closed. It's kind of interesting. And it's like, you should retake this picture if it notices that somebody blinked. That's really cool. And so that's artificial intelligence. That was a little tiny processor inside of the baby camera trying to figure out where heads are. That's a human-like trait, right? Notice where people are. But it was able to do that from the video feed or the image feed that it was getting from the lens on the camera. So that's cool to think about. So it's machine learning, and now I need to teach you, like, how did they make this program to detect faces, to detect eyes, and see if they're blinking or not? It is machine learning, and I need to teach you how machine learning works, all right? Because that's probably the most popular subfield of artificial intelligence. All right. So this has a lot of words. It should make sense once I finish saying the words. All right. So machine learning is the idea of teaching a computer kind of like you would teach a human, right? You give it like problem sets and homework and stuff like that. So what you do if you want to make machine learning software, like you want to make ChatGPT or you want to make a blink detection program, even facial recognition program, what you do is the first thing you do is you gather a bunch of what is called training data. If you're trying to detect people blinking, you will gather a bunch of pictures of people, either blinking or not blinking. Does that make sense? Because then you're going to give that to the machine to learn. That's kind of the idea, all right? You make a bunch of training data, and you'll label that data with what you want your machine learning program, which is called a model. We call it a model to learn, all right? That's just your machine learning program. At the end, you call it a model, all right? We're training a model is what we're saying, all right? And so if we're trying to notice at least faces, not even eyes yet, if you want to notice where the faces are in an image, you will give it a bunch of pictures of like faces with a bunch of faces in it, and like you've drawn the box already, you figured out where the faces are, and then you'll also give it a bunch of pictures of things that aren't faces, because you don't want it to hallucinate, right? You've heard that term in terms of AI before. You don't want your model to think that there's a face in an airplane or something, right? Don't want it to go looking for weird things. So you're going to give it a bunch of pictures of faces and non-faces, and you will label it. This picture has a face, has a couple faces, and here they are. And then this picture has no faces at all. So it can eventually learn the difference. Does that kind of make sense? It will figure out the difference if you give it enough examples, all right? And then same with like if you're trying to detect blinking as well, you will also give it not only pictures of faces, but faces labeled with eyes open and faces labeled with eyes closed. So like that's a lot more information you're also going to give, all right? So like you got pictures with eyes open, pictures with, I don't know, eyes closed, somebody sleeping. Open, eyes closed, and then a bunch of airplanes and plants and things, right? And you've labeled it. That's it. And then there are algorithms that can take that stuff that you've labeled and learn how to detect the difference. That is wild. That's something I can't teach you here. It's very hard to teach in a CSCI 1 class, but if that's something you're interested in, talk to me. I can show you how to learn it. But that's what you do. You get a bunch of training data, and that's honestly the hardest part, usually. And then you train your model, right? That's your program. We call it a model in machine learning, using some kind of machine learning technique that's able to take this training data and understand the difference between the things. So one way that's very popular is called neural networks. That's a machine learning method, technique to learn from training data. All right, there's that. And at the start, once you start training your model, it's like a baby. It knows nothing. Usually it's very horrible. It's like thinks that there's 50 faces in a picture of an airplane. Like it doesn't know the difference. But what you do is you keep running it and you have it correct itself. It's a bunch of rounds that it goes trying to train itself on the data. It doesn't just look at it once. It looks at it a bunch of times. And eventually, with enough computational effort to keep training it and showing it the difference between things, it will learn where the faces are, where eyes are, just like because you've given it those things, it will figure it out. Isn't that wild? And we still can't really explain how it figures things out. It's like we have these methods and it just kind of does it. That's interesting to think about. Right? So there's that. And yeah, just to make sure that you've done everything right, once you have the model and it's like kind of working good on your training data, you will also have kept a little bit of the data aside secretly. Like a bunch of faces and airplanes and people blinking and not blinking. A bunch of stuff that the model has never seen. So that you can verify that it didn't just memorize the training data, because that's not what you want, right? You want it to just be able to work in real life too, right? On any picture of people. So that's what you do. You test your model in a separate set of labeled data where you know the answer, but it has never seen that before, just to make sure it didn't memorize the answers from the training stage. And just make sure it's doing the right thing, and then you put it in your camera. That's how it works. All right. Isn't that cool? That's a fun idea. Just kind of learns. It's wild to think about. Any questions about that so far? Have we heard these ideas before? These terms? Are they new? Hopefully they're new to some of us. But yeah, for example, what a neural network is all about, it's like a virtual model of how a brain might work. So a neural network has a bunch of virtual neurons, and it's passing information around, which is fun to think about. Like this is where the information comes in, and like it's like wiring up little virtual neurons. That's what a neural network does, and I'll show you some more of that soon. But inside the computer, at least, it's not like electrical signals like your brain has, and like visual things that are turned into electrical signals from your eyes or something. It's just a bunch of numbers that are being passed around essentially inside of a neural network. Just like, all right, it's getting input 1.0, and then somehow it's passing it along to here, and now it's now it's like native 3.5 down here. It's like it's combining the numbers in a weird way. It's just kind of adding them together and multiplying them, essentially. It's like, all right, the input here is like the sum of these times something plus an offset, and somehow the answer is 3.5. And like the numbers eventually mean something. It's like maybe a high valued number means a high positive number means there was a face and the eyes were open. Maybe a negative number meant that the eyes were closed. I don't know. But that's what you train. You're trying to create numbers and interpret the numbers at the end of the day, at least inside of neural networks. But yeah, how do you turn a picture into a number? We'll get into that. But yeah, step 1 is honestly the hardest step, if you want to think about it. Step 2 does take a lot of money, but I mean, companies have the money. Step 1 is hard for anything that you want to do, because it's very hard to get a lot of good labeled training data. Like people have to set aside a lot of time. You need like millions of pictures if you want to do it right. So it's very hard to get good training data. And now you know one reason why Instagram and YouTube will like store your photos and videos for free. Because they're going to use it to train their things. And then also Google Photos back in the day, that used to be free. They let you put as many pictures on that as you'd like, because they were training their AI classification models on the photos that you uploaded to Google Photos. But now it costs money because they got them good enough. They got enough pictures, right? So yeah, that's fun to think about. All right, does that make enough sense? So I have an exercise for us. I'm not going to test you on it or anything, but I think what I'd like to do next is, yeah, eventually I'm going to give you an exercise. But just to get there, let's kind of talk about neural networks some more. I'm going to teach you some terms. I will not test you on these terms. But yeah, this is like the most popular way to do things, is what ChatGPT is powered using. But a neural network is the idea of like pretending that the computer is a brain. Right? It's got a bunch of virtual neurons that we say. All right, a bunch of virtual neurons, and then maybe like, I don't know, it's got some inputs, 1.0, 2.0 or something. And the idea is that these little virtual neurons are like propagating numbers. And so like there's an input layer, we say, and an output layer, and there's a bunch of things in between. It's just a bunch of numbers being shuffled around, doing a bunch of math, essentially, right? And there are, we call them weights on each of the neurons. Like maybe this one eventually becomes important, has a high weight, like weight 5. So it's going to add up what it's getting, like the 1 plus the 2 to make 3, and then multiply it by 5. So it's like its answer is 5 times 1 plus 2, and that's what it gives back to the person. Like that's what it sends down here. And eventually it will learn the right weights to treat things properly. It will learn the difference between like planes and faces and things like that. All right. So yeah, you might wonder, like, how did they do this? How did they do the blink detection, the face classification? That would involve, right, if we're going to do a bunch of stuff with numbers, that would involve turning a picture into a bunch of numbers, right? How do you do that? Well, here's one example. Here's a simple idea. If you want to learn more about this, there are some cool YouTube videos that I can recommend. But like one of the quintessential examples of machine learning is to do digit classification. Like look at like the Postal Service uses this, right? Like this is a digit. It's got some pixels. Like what number was that? Of course, we see 8, but you have to learn the difference because some people draw their 9s like this, some people draw their 9s like this, right? You have to learn the difference. How do you do it? And so you have to turn these into numbers, right? And essentially, as input, you give every pixel of the image separately. And what number it becomes is, if you want to convert it to black and white at least, the number that it becomes as input is like a 1 if it's black, a 0 if it's white. Does that make sense? That's how you can turn a picture into an image. It's like figure out the pixels, and if it's gray, it's like 0.5 or something. I don't know. You can do the same with colors. Just like take every single pixel, all like 780 of them in this example. You can imagine that like AI that's generating images is doing a lot more than that. It takes a lot of space. And like that's being propagated as a bunch of numbers across these neural networks with a bunch of layers and neurons in between. And then the output layer, at least for this one, is like, it's computing numbers still, and it's like how much it thinks that this is a 0, how much it thinks that this is a 1, how much it thinks this is a 2, all the way to how much it thinks is a 9, 8 or 9. And you can imagine that like with enough numbers being propagated around, that the one that's going to like light up with the highest number in the output is going to be the 8 if you trained it right. Does that kind of make sense? That's what happens. Just sending numbers around until like it's going to get to the output layer, and like maybe the weight here is like 0.5, this is 0.7, 8 looks kind of like 9, so maybe it's like 1.5, but 8, this one that's meant to mean 8, it like fires, it's like, all right, this is like 5.5, I really think it's an 8, and then you take the one it thought that it was the highest. All right, so that's kind of what goes on. That's how you send pictures into things, into a neural network, and get information back, kind of, right? So with that idea, here's just some silly examples and some things for you to try if you've never tried it before, all right? So let's see here. So please, if you've never done this before, it's worth trying. So I'll give you a few minutes to play around. Please go to crayon.com, and the crayon is with AI in it. Hee. This is just an image generation app. And so if you go here, crayon.com, we can just stay together, I think. Feel free to post what you find on our Discord or something, but let's see, you can ask it to draw stuff for you, all right? And so here, I can ask it to draw, I don't know, a cat, I don't know, a programmer cat typing code on a laptop. I don't know, something like that. And it will go and draw things for you, draw pictures of what that thing's like. But you give it a little text prompt and it produces an image. Does that make sense? We've used these before probably, right? Like if you use that, have you thought about like what kinds of training data is it going to need? Like somebody made this AI software. What did they train this model on? This thing that was taking our text to images. What do you think? Please try it as you're thinking. Like, what kinds of training data do you think they use? How did they build this website, this AI model that generates pictures from text? Well, look at it. I got my programmer cat. Code in the background. And it gives you a few options, of course. Oh, those are a lot. I love it. It's beautiful, right? And you can have whatever you want. But if you think about it long enough, it's taking text to images, so it must be trained on a bunch of images that are labeled with like paragraphs of information about those images. Like it's got a bunch of pictures with cats in the image, right? And it's got descriptions of those images saying, all right, there's a cat in this image, there's a cat in this image. So not only does it learn like English, it's got to learn like what a cat is based on that. Does that make sense? Like it's being trained, this has to be trained on a bunch of images that have descriptions, yes? So they can learn like, all right, the images that have cats in them, what does it mean to be a cat? That's what it needs to know. What does it mean to be a programmer? What does it mean to be a laptop? It's learning all the words with the descriptions of the images, and then it's able to reproduce them. Does that make sense? Isn't that cool? I love it. So play around with that. Hopefully you found some cool images. I think this one works still. Uberduck.ai. It used to be easier. There were other websites that did this for us, but like this is like speech generation. You could type something and have it talk like a character. Is there SpongeBob here or something useful? Yes, SpongeBob. I love computer science. Whee! Is this going to actually play? Honestly, don't know. Hopefully it's not loud. Sorry if it's loud. I don't know if it's actually playing or not, but this is, again, it's called Uberduck.ai. Let's see if I can get it to play on my own. Alright, I can't figure it out. It's making me buy it. Apparently, it probably played it, but I didn't have my speaker. Like, there's something wrong with the speakers in this room. But, like, this is a website where you can type something, and it can talk like SpongeBob or some other character. And so, how did it learn that? You can imagine, right? What was it trained on? It was trained on all the audio of SpongeBob matched to, like, the subtitles of what he said. Does that make sense? So it learns how SpongeBob says this word, and it can extrapolate other things. Like, I don't know, he probably said all those words. It can, like, talk like a human, talk like he might have talked. That's so cool. So maybe you can get that one to work. I can't get it to work. And then the last one, this is the real one that I want to like spend some time on for a second. It's called playground.tensorflow.org. Please go there one last time, and I'll show you what to think about. So it's playground.tensorflow.org, and it's this website. And let me explain it. This is finally you like really doing something with neural networks. So what playground.tensorflow.org is all about is it's kind of teaching you how to make a neural network. All right. So here on the left are a bunch of different data sets that have orange dots and blue dots. And the goal, you can keep it on the first one if you want. The goal of this example is that you are creating a neural network with a bunch of layers, however many you think you need, I don't know. And then the output, like what it's trying to do, what your program is supposed to be doing is determining the difference. Like where are the blue dots versus the orange dots? It's trying to, like, it's getting as input coordinates. Like this is 0, 0, this is, I don't know, 0, 1. It's getting the coordinate but not the color, and it's trying to predict the color. Does that make sense? That's what this wants to do. And you can have it learn the difference between the blue dots and the orange dots by adding a bunch of features. X1 is the x coordinate of the dot, x2 is the y coordinate, x1, 2 is the, I think, oh, this is disgusting. It's the x coordinate squared. This is the y coordinate squared. They like to use x1, x2, x3, stuff like that. That's a squared, the second thing. This is x1 times x2. That's that. If you want to turn it on, it'll use that as input. Right now it's turned off. And then this is the sign of the x coordinate. This is the sign of the y coordinate. It's like taking those pieces as input. Can you predict if it's blue or orange, your dots? And you click play, and it tries it, and it tries to learn the difference. See how it's learning the difference? It's like, I have no loss. I have done it to 99.9% accuracy. And then you can eventually stop it. Does that kind of make sense, what it's doing? It's trying to learn. It's taking as input some of these things, which are coordinates of dots, or like squared coordinates of dots, or things like that. And it's trying to learn the difference between the blue dots and the orange dots. It's trying to figure out where they go. It's trying to classify them, we say. All right? So see if you can figure out the right combinations of like the dots, or like try to add enough features and hidden layers in neurons and things to correctly find the difference between all these things. The checkerboard, these blue and orange dots, the swirl of blue and orange dots. See if you can find and get it working. My challenge for you, though, is not to like spam the plus button. See if you can get it to like, see if you can train your neural network to determine the difference with the fewest number of neurons and inputs. All right, that's my challenge for you. I'll give you a minute to try it. But it's fun to think about. This is playground.tensorflow.org. And as you're trying it, are there any questions about what it's doing? Did I explain it enough? It's kind of hard to explain since there's some math involved that you can use behind it. You can get it working if you just like add as many neurons as you can and as many layers as you can. Let's see if you can get it with the smallest number. There it goes. And then also, as it's running, you can see which of the neurons became important. It noticed, it learned that this neuron right here was very important. Like it gave it, you can see how it's making it thick lines. Like this one is very important at determining where blue dots are. This one's very important at determining where orange dots are. Things like that, which is useful. Like it's got these weights involved. Very important, very important. And the final output is just like, was it blue, was it orange? Maybe it's trying to like calculate 1 if it was orange, 0 if it was blue. Something like that. That's what it's doing, just sending numbers around. Yeah, try it for all of them. Did anybody find a way to do it with not many features to do the circle? Like to determine the difference between this one, the upper left? How many neurons did you use? What's the minimum number to get it to work properly? Can we find it? Yeah, please keep playing around, but I'll tell you a secret now. At the end of the day, right, what separates these blue dots and these orange dots, so let me teach you why you might want to study machine learning rather than just like adding neurons and wasting computational time to add a bunch of neurons, right? The fewer the better, the easier it is to train. What's the difference between the blue dots and the orange dots? It's like a circle, right? There's a circle separating them, if you think about it. What is the equation for a circle? It's x squared plus y squared equals r squared, right? That's the equation of a circle. Which features look a lot like circle numbers? Because like when you're propagating information, remember that it's going to do this. It's going to like take some numbers and add them together and do things. So essentially what's happening here, like you give it, maybe you give it 1 and 2 or something. And then as it's feeding into the neural network, these are going this way, I don't know. This is going this way. It's doing math on what it's given, and it's also adding them up. So like if this was 1 and this was 2, like this next one is taking it just from this one. And so it's going to do some sort of mathematical function on 2. But this one, if it's taking both these guys, 1 and 2, it's going to do some sort of mathematical function on 1 plus 2. It's going to kind of add them together, all right? That's what's going on there. And so with that in mind, as input, if you just give the x-coordinate squared and the y-coordinate squared, it will add them together just by propagating it. If you think about it, you don't even need any output layers. Like there's one output thing. It's like either it's a 1 or 0. So it'll take this guy, add it to this guy, and compute like, right, what that radius should be. Watch. Ta-da! And so that just saved your company millions of dollars training it because you use like 2 neurons instead of 52. Does that make sense? That's why you might want to learn machine learning. Isn't that cool? Are there any questions about that idea? I know this is very complicated, but if we understand any of it at all, I'm happy. Do we get it working for the other ones? We train it well. So what about this one? This is, this one is like a checkerboard pattern. If it's getting coordinates as inputs, do you see how that if you multiply the coordinates together, like x times y, here it's positive, and if they're both negative also, it's also positive down here. If you multiply their coordinates together, here it's negative for the orange dots. So if you just took the x and y together and multiplied them, again, you only need that going straight to the output. It would learn the difference very quickly, rather than using any extra neurons, artificial neurons. Isn't that fun? I will not test you on this or anything. It's just fun to think about. And then also, all right, next one. What's the difference between these dots and this dot? There's a line that separates them, right? So we kind of want to learn the equation of a line. Y equals mx plus b. So that's pretty much y and x together. Y plus x. Solve for y. See how it learns the line? So yeah, there's ways to make it fast. And the fewer neurons means the less computational power to train the model. That's really cool to think about. The swirl, though, does not look like any kind of like mathematical anything. I guess sine is kind of wavy, so that helps you with swirling, but it's not perfect. So you kind of do need to just like give everything. This is where you spam neurons to learn the swirl. I don't know. Because this doesn't really look like any sort of mathematical equation. It's like it's looking a little weird, but with enough neurons and enough time, it's going to suddenly learn the difference, right? It's like jumping all around. This is a hard one to learn, the difference between. But it's like a face, right? You give it enough time, it'll figure out the difference. It does take enough neurons, and you can kind of see what it's learning. Like, all right, this neuron is trying to learn this blob of a difference here. This neuron is really focusing on the very center for some reason. This neuron, it really likes like the middle, like an hourglass kind of shape. They're all trying to focus in on different ideas, and yeah, with enough time, it'll probably zero in on the answer. Maybe I need more neurons. I don't know. I can have 6. I can have 8 here. But yeah, you kind of just need to spam it, and then it'll get it right. Try again. And then, of course, it's slower. You see how it's much slower to do this right now. It takes more computational power to do it right. But yeah, that's neural networks in a nutshell. It's taking numbers as input. It's learning which neurons are important. Like each neuron is trying to focus in on different things, learning different parts of the picture, for example. And yeah, eventually it will become happy and like flatten out, get as good as it can get with enough neurons. But if you throw enough neurons at the problem, it'll eventually learn it, is the moral of this story. And that's how ChatGPT became a thing. They gave it billions of neurons, and it's able to learn English. Cool to think about. All right. So yeah, it's getting better and better. It's almost there. Any questions about this? Does this make enough sense? It's a weird little idea. Just a bunch of numbers being passed around, trying to model it like a brain, though we don't know too much about brains still as humans. But it's getting there. Ooh, it's doing better and better. The loss means it's failing less with a low loss. There it is. It's got it. It's almost got it. It hasn't learned it perfectly. It still thinks that like there's a little gap right here. Like that. There are no blue dots there, so it's fine. That's why you want to definitely have a testing set to make sure it's not like memorizing things. But yeah, that's neural networks in a nutshell. Hopefully that makes enough sense. Please ask me about it. It's very fun to talk about, but it is a little complicated. All right. So yeah, for the last things I want to talk about today, let's just like talk about applications of AI now. So like car factories, if you want to make robots, you can train them using AI. You can train a machine to do a job, and it can notice things that like you can give it a video feed, it can figure out where the parts are now. Machines can do the same thing over and over again and not get tired, right? And so they're very good at this kind of thing, like building a car and being very precise about things. So there's a very small chance of failure and breaking down, and they work a lot faster. Like you don't have to pay, right? You have to pay a robot either. It works faster and more precisely than a human could. And so robots are, in this era, like they're taking humans' jobs. This used to be a human's job, right, on the factory line. But now we've got robots being programmed to do the same thing. They do cost a lot of money to set up and maintain, but I guess you're getting rid of salaries at the same time. So there's some give and take there. In theory, they'd find a new job for all the people this is replacing, but sadly, capitalism does not work that well. But that's factory robots. That's a thing. Maybe we've experienced some of that. There's also just like general intelligence. This is probably what you think of. Have any of us remember watching, or have we seen like recordings of the supercomputer playing Jeopardy? Is that a thing that we remember? It is not the most recent, but it was called Watson. It was made by IBM. It's a supercomputer, and it went on Jeopardy and answered questions. It's like it was able to understand English and respond with answers. And that's kind of what we think of usually. If you think of like a computer being smart, being artificially intelligent, you think of it like being good at a game show. And so this is a great example, I would say. So Watson was a supercomputer. Probably still is. It was made by IBM. They started on it back in 2005, so they could make it better now if they haven't. Things have gotten faster. But what it does is, you kind of know the Jeopardy game, hopefully. Like it's a question, or like it's an answer, and you discover the question, kind of thing. And so it's just like you're given English, and you have to respond to like a trivia question in English. And so it has to understand, it has to use natural language processing to figure out like what was being asked of me right now. All right? And so it has to break down sentences. So it's like, just like we learned how to do it in grade school, like the supercomputer, even ChatGPT essentially is doing this, like it's breaking it down to like subject and verb, like what is this question asking me? And trying to determine the answer to the trivia question based on that. It's trying to understand it, right? And it's got a giant database of information on the back end. Like they took it and they brought it with all the natural language processing abilities, and then every database that it's ever like trained itself on. Like, so when it went into Jeopardy, it had a copy of all of Wikipedia. It probably had a copy of every public domain book ever written, things like that, more than a human could ever keep in their mind. And it just kind of blew people out of the water because of that. Like, it was so good at answering the questions once they tuned it right. But kind of what it did is it like parsed the sentence, like subject, verb, what am I being asked? And then it comes up with, just like the digit calculation thing, kind of comes up with a bunch of potential answers. Like, all right, the answer to this question could be answer 1, answer 2, answer 3. And then it has like probabilities. I think that it is, I don't know, I am 91% accurate that this would be the right answer. 85% chance it's this answer. Maybe they don't add up to 100 or something, but like it's going to go with the highest one if it's like above the threshold. It's like, all right, I'm 90% confident that it's answer 1, so I'm going to respond with answer 1. Something like that. That's what it did. All right. And so it went on Jeopardy as well as other places, and it had all of Wikipedia, had all of all of the internet essentially, as much as they could save away. And it was so fast. It was beating all of the professionals, all the people that have won Jeopardy in the past that were very popular. So yeah, that's a fun YouTube video to watch if you want to. But like that's probably the first example that we had as humans of noticing a computer being like artificially intelligent. Like it was smart and it did well at a game show. All right. So that's how far we've come. And now of course we have ChatGPT, which is an even better example. But yeah, at the end of the day, it's just like you pick your training data, you learn how to do things. You learn what English is like. You learn how to answer questions. So you can imagine that Watson was trained on a bunch of Jeopardy subtitles or something. Old shows, old questions and answers. So yeah, the last major example that I want to give today before I show you something for your essay is chess. Chess and Go, the two games that are very popular. So back in the 90s, at least when artificial intelligence was a thing, when computer science was a thing, like we had computers, like the pie in the sky dream of the people in the 60s was like, let's make a computer that can play chess and beat the grandmasters at chess. That was their dream, and we achieved that dream back in the 90s, right? It's crazy that it's so long ago, but that was a thing that they were chasing for decades, and now it's just like some of you are younger than this thing. So it was 97 when a computer, an artificial intelligence program, beat the current world chess champion at the time. All right, so that's crazy. What it did It wasn't even a neural network, I don't think. What it was doing is, if you train a computer to play chess, what it thinks about is all the next possible moves. Like, here's what the game board looks like. What the machine learning, what the artificial intelligence software did was, like, it tried to think about what are all the moves that could be made right now. Like, this move could be made. It tried to also think about the likelihood of those moves being made. Like, all right, the game board could go like this. If the guy makes the move this way, like, you can make the move this way, make the move this way, and then the board would look like this. Or you can make this move, and the board would look like this. And then it keeps going. Like, all right, if they made this move, what are my options now? Dun, dun, dun. So it builds this giant, it looks like it's kind of like a tree. We call it a tree. It's like the roots of a tree, right? Of all the ways, it's branching off, all the ways that the game could be played. And it has memory for that. And so it's able to think like 5 steps ahead if it needs to, and figure out, like, all right, if I make this move, then I can trigger this reaction, things like that. But with enough memory, you can do that. I hope that makes sense. Like, you can plan out the game, and it's like you can enumerate all the possibilities, and you can think farther ahead than a world grandmaster could, world champion, and you can come up with the right strategies, right? So it's very cool to think about, and it was 97 when we made a machine learning program that was able to do this kind of thing and beat the world champion. There's also another game. It's an Asian game called Go, if you've heard of that. It is it's kind of like chess, but on steroids. It's like more complicated, it has more pieces, and so it took a computer until 2017 to finally beat a world champion at Go, and that was like a huge upset. Have we heard about any of those ideas? Is that just me being interested in it? But it's the same idea. Like, you're enumerating all the different ways that the game could be played at that point. It's really cool. But the really fun reason, a really cool reason why, like, these are important problems to solve, is because these games can be played alone, more or less. Like, what you do, right, is if you want a computer to get really good at chess, do you kind of see how you can have it play itself? Because you don't need any human input. It's just like, you can make this move or this move, like, try the possibilities, right? So the rules of chess, the rules of Go are very clear, and so you can have a machine play billions of games with itself and get better and learn strategies that no human has ever come up with. Does that make sense? That's really cool. That's the reason it can get better than a human. It can, like, figure out these weird things that humans have never noticed, because it can play so many games, more than a human has ever played. Cool, right? It can keep playing against itself and get better and better and better, and reign supreme because of that. All right? So that's how you can essentially teach a program to do something. If you have, like, a game that has a bunch of strict requirements, like chess or Go, you can teach it, all right, here are the rules of the game, go play yourself 1 billion times. When I wake up tomorrow, show me what you've learned. And so it can learn its own strategies. It's really fun to think about. Really popular topic, so if you ever want to get into computer science, this could be a field that you study. Cool. Any questions about these ideas? So yeah, you know the implications now, I hope. In the remaining 3 minutes of class, I'd just like to give you just like a little example of kind of what I want for your next essay, because it's like 1,000 words, you're finding stuff on social media, it's kind of a little hard because it's open-ended. So here is an example. So if you're struggling to find examples of fallacies, my recommendation is, like, to go on Facebook, go on YouTube, go on Twitter, whatever it's called now, to pages of news websites. When they're posting articles, a lot of the time those things that they're posting are, like, their stories are controversial, and people in the comments will be angry, or they'll make fallacies in the comments. That's a great place to look, right? Or go to any, like, political person. Go to, like, presidents, vice presidents, ex-vice presidents, ex-presidents. Like, here's an example of a straw man fallacy that I found a couple years ago. So here is a straw man fallacy example, and here's kind of what I would want from you in your essays. Like, all right, here is a post from Vice President Kamala Harris when she was vice president still. She made a little tweet on International Women's Day. It was like, I want to honor the women who have, this was during the pandemic, I want to honor the women who for over a year have gone to work, often risking their health to protect us, all these people, thank you. And then Dave here responded and is like, just the women? Guess that would be typical of you. I thank all who have risked life for others. And so Dave, Angry Dave here, is a great example of a straw man fallacy, and this is kind of what I want from your in your essay. You give the context, give the tweet or whatever, and you'll say this is an example of a straw man fallacy because Dave here is putting words in the vice president's mouth. Vice President Harris was saying, like, she was thanking women because it was International Women's Day. She was not saying that I'm thanking women and not men. She was just highlighting women because it was International Women's Day. She doesn't have anything against men, like Dave is implying. He's putting words in her mouth, therefore it's a straw man fallacy. Does that make sense? That's what I want to see from you. Okay? And yeah, that's pretty much it. So that's kind of what you can look into. Politics, very controversial, of course. It's a very easy place to find fallacies if you're struggling to find some. But yeah, I think that was my example. That's kind of what I want from you. And so I want you to find 5 of those kind of things. All right? And I think that's where I want to stop today. So if we're good, we have no questions. That's all I got.